Greetings and welcome. Talking about probabilities of independent and dependent events, part 2 video. Here's example 5 from your Big Ideas math textbook. Algebra dose. You randomly select 3 cards from a standard deck of 52 playing cards. What is the probability that all 3 cards are hearts? All right. And then there's 2 scenarios. One is with replacement. All right. And so with replacement, this would make that an independent situation. And then part 2 is you do not replace. And so as a result, whatever card you selected as your first is no longer in the deck to be picked for the second card or then the third card. And so as a result, the events change the possible outcomes of their subsequent events, and these would be this would be dependent. All right, and so as a result, let's see if we could figure out these probabilities. So 3 cards that are hearts, and so hearts are one of the 4 suits in a deck of 52 cards, and 52 divided by 4 happens to be 13. There are 13 heart cards. And so the number of successful ways that you could get a heart for your first card is 13, as well as for the second card, as well as for the third card. And the total possible set of outcomes was 52 for the first draw. Because we put that card back, there's still 52 in there, and 52. And so if I want to figure out the probability of these independent events, I can simply multiply these. And it turns out if you multiply and cross-cancel and simplify, you get 1/64th, which is approximately 1.6% is the likelihood of that occurring. Which, wow, doesn't feel that likely. And so I've hardly ever played poker, but that certainly makes me think about, like, wow, just getting 3 hearts is pretty hard thing, and that doesn't necessarily mean that they're going to be in a row. So for dependent events, for the first draw, the likelihood or the number of ways I could successfully draw a heart, there are 13 to pick from. But now the second card that I draw, there's 1 less heart, and so there are 12. And then the third card, there are now 2 less hearts to draw from. And so those have reduced by 1 each time. As far as the total possible outcomes, the first draw, there were 52 in the deck. But the second draw, there were only 51. And the third draw, there were only 50 cards. And so as a result, the probability of those individual draws had changed. And now, if I multiply this out and cancel out, however you do it, you could write multiply across, get one, big numerator, big denominator, divide it out. The reduced version happens to be 11 out of 850, but you can write that as 1.3%. And so notice the percentage is less because, partly because the number of hearts I could pick from were less with each subsequent drawing. Let's see. Ooh, here's a follow-up question. What is the probability that none of the cards drawn are hearts? Well, let's see. So probability not heart. I'm suspecting I could find the complement of that. I'd want to say, no, it's not quite. If I did the complement, if I did 100% minus 1.6%, that would be the probability that I didn't draw all 3 hearts. This is slightly different. They don't want any heart for any of those cards. And so that's a little bit different. So for part A, with replacement, so it's independent, the number of not heart cards would be, let's see, I wanted to say 39? Yeah, 39. So there are 39 not hearts in the first draw. If I replace it, there's still 39, then there's 39. and there were 52 each time, and so I would multiply those out. And yeah, we'll calculate it. We'll calculate it. Why not, shall we? And so if I multiply all that out, I get 27/64, which is about 42.2%. And so notice that wasn't the 98.4%, which the complement of that event would have been. 98.4% is the probability of not getting all 3 hearts. This was the probability of not getting any hearts, which would include a single, 2 hearts, or 3 hearts. And so there you go. There you go. Let's see. And then with replacement, I'll write out the dependent setup anyway, but I gotta keep rolling here. So were there 39 not hearts, and then there would have been 38 not hearts, and then 37 not hearts, and the denominators would have been 52, 51, and 50 respectively. All right, I'm already here. I happen to have, if you multiply all that out and simplify, you get 703 over 1700, which is approximately 41.4%. Boom. Aha. All right, let's take a look at example 6, shall we? Aha. All right, this is interesting. So here we go. A quality control inspector is someone who checks for defective parts, all right, coming out of like a factory or something. The table shows the results of the inspector's work. Find A, the probability that a defective part passes, and B, the probability that a non-defective part fails. All right, and so let's say I have, actually, I'm gonna copy this and paste it over here, and I'll draw this up separately each way. And so we're assuming that we already have a defective part, and so my possible outcomes, I'm looking at just the defective parts. So the denominator would be 3 plus 36, which is 39. And if I want to consider, in this case, success, this is actually a worst case scenario if you're a quality control inspector. Which of these did we consider as a pass? And so 3 of those were a pass. And so if we divide that out, I get 1/13, which is approximately 7.7%. And so this is typically we would call this a false positive, is one way you could describe it, where we were labeling something as a productive, passing, functioning part, and it wasn't. And so this is kind of, you don't want those to get out to customers, and unfortunately they did. 3 of those broken parts were sold, will be sold to customers as functional. And so those are going to be your complaints coming back. And let's see, part B was, what's the probability that a non-defective part fails? And so I'm assuming the conditional probability here, it's a reduced set of outcomes. I'm looking at just the non-defective parts. And so my total possible outcomes there, the denominator is the 450 plus 11, which is 466 when I add those together. And what am I calling a success here is a fail. So that's weird. And so the number of those non-defectives that failed were 11. And so 11 out of 466, no, 461. Let's see, look at my sad scribbling strategy. 461 is about 2.4%. And so we would describe those as false negatives, is one way you could describe it, in which you would say, right, those were functioning, but we labeled them as failing. And so that's not great, because those were perfectly good products that now you're throwing away, recycling, reusing parts of to rebuild. But it would be lost time, lost materials. But at least your customers won't be complaining about those, right? And so as a business, you'd rather throw those away and keep, your company's good name and quality of your products high. Like, that's still a better overall thing. This is the scenario that you don't want, right? So let's see. An example, find the probability that a non-defective part passes. No, I'm gonna, for sake of time, I gotta keep cruising. I'll skip that one for now. Here we go. All right, finding a conditional probability. At a school, 60% of students buy a school lunch. Only 10% of students buy lunch and dessert. What is the probability that a student buys lunch, who buys lunch also buys dessert? Okay, and so 60%, so let's see. So I want the probability that someone who buys lunch also buys dessert. So I'm trying to figure out the probability of dessert given they buy lunch. Let's see. And so one of the ways I could figure that out is I'm going to do the probability of A and B divided by the probability of B. And so we've got, what do I know? Let's see, does it make sense for me to use green and purple in this instance? Yeah, kinda. So the probability of someone buying lunch and dessert, they had already given us, that's the 10%. And so my numerator is 0.1. And the people who buy just lunch is the total sample space, is the 0.6, right? And so if I divide that out, I get 1/6, which is 16.7%. All right, and so 16.7% of lunch buyers also bought dessert, is one way you could say it. But only 10% of the student body bought lunch and dessert. Okay, good. Here we go, last question. At a coffee shop, 80% of customers order coffee. Only 50% of customers order coffee and a bagel. What is the probability that a customer who orders coffee also orders a bagel? And so here's another kind of conditional probability thing. So what's the probability that someone orders a bagel, given that we know they ordered coffee? And so this is going to be equal to the probability of both divided by the probability of just getting coffee. All right. And so the probability of both, notice the word and was our 15% there. So I guess I'll write it over here so my equal sign kind of lines up nice. And the probability of just coffee was 80%. So 0.80. Didn't need the O there, but it felt like I was on a roll. If you divide that out, you get 3/16, and that's approximately 18.75% for the probability here. And so this is the 18.75% of all or of coffee buying customers get bagels, is the way you would think about that. While 15% of your entire customer base gets coffee and bagels. All right. So anyways, thanks for watching. Hope you have a great day. Bye-bye.